So let's take a look. If you had f of x equaling 3, in other words, that means y equals 3, correct? What does that look like? If you were to graph that? At y equals 3, it's a straight line. Which way? Horizontal. Do you agree that's what that particular graph looks like, correct? And I'm asking you for a general equation that will tell me the slope at any point on this line. Right? What's that answer? What's that slope? 0. So this, if you have a constant, do you see how this is a constant? Why do we call it that? Because it doesn't have a what? It doesn't have a variable. The derivative is flat out always going to be 0. Because that is the slope of the tangent line at any point on there. Okay? Doesn't matter which point you have. Once we do power rule, I'll go back up there and show you that power rule really works for that one too, if you happen to have a bad day and you forget. Right? Power rule is the one that could have saved you a ton of time up until now. Because remember, when we did 3x squared before, we'd have to put x plus delta x in, square it, subtract the function, divide by delta x, FOIL it out, do all that fun stuff. Well, the power rule simply says if you want to find the derivative, all you need to do is take whatever the exponent is and take it times the coefficient. So 6. Then you write down whatever variable you have, which is x, because these are with respect to x, right? And then you take whatever the exponent used to be and you subtract 1 from it. So it was 2, subtract 1, and you get, there's your derivative, you're done. Okay. Is it? Oh, the shortcut you figured out? Okay. Or I think we just did x squared one time in class and that we came out with 2x, right? I mean, because that's what it should be. Okay, and so you don't have to do all the work, but remember, f prime is still that. Yes? Yep, subtract 1 from the exponent. Now, how does that work here? Well, really, you could look at this as 3x to the 0, correct? That's how you could write this original one up here. 0 times that is 0. Who cares? You bring it down a power, whatever. It's still 0 times something. It's still 0. Okay, so power rule really works for that one, too. But I wanted to give you the conceptual look at that. Okay? Now remember, this is a parabola, right? If I were to graph this original. And so you still need to know what x value you're talking about. Obviously, if I'm talking about this for an x value, I have to plug that x value in here, right? To actually find the slope. Or if I'm talking about this x value, I think you should know the answer to that one. It'd be 0, right? So keep that in mind that you still have to put in whatever x value you need to find the actual slope. But derivative is a general equation that will tell you the slope at whatever x value you substitute in. Oh, you remember how much fun 1 over x was? Imagine how much fun 1 over x to the third would be. Doing it by hand, by the definition. Do you agree that could be somewhat painful?
Yes.
Well, we're going to get a little sneaky. We're actually going to use power rule, but when you use power rule, everything's got to kind of be on, let's agree, this is kind of the normal level we're used to working with algebra, right? Not in the denominator. We'd rather not work with it down there if we could get away with it. Well, there was an Algebra 2 topic that we did that I told you was going to be hugely important. It's a nice little trick. You make it unhappy. Right now, x is pretty darn happy because the exponent is positive, correct? Well, unfortunately, we're going to make it unhappy. And so this is the same thing. Well, if I put x in the numerator, it makes it unhappy. So how do you have to write it? Do you agree this 1 is still up there, correct? I didn't have to move the 1, right? Then there is something still holding the place of the bottom, but it's a 1. So that's the beautiful part. I don't even care about that anymore. There's a 1 down there. Hey, it's fine. So do you agree that that's really just saying this in that case? Now, have I taken the derivative yet? No, that's still just the original, right? And so now we have to go and take the original. The reason you know that is I never wrote f prime. Right? That's how you know I didn't take the derivative. Now you can use power rule. And again, what's kind of understood to be out front there? Yeah, just a 1, right? And so we can take -3 times the 1, which is obviously -3 x. And here's where people make a mistake. -4. You subtract 1. -3 minus 1 is -4. And I would suggest that you do fix that. And this is also why I took so much time in making sure you could fix that in Algebra 2. Of those pieces, do you agree have a -3 and you have an x as bases? What is the power on the x? It's -4, agreed? What's really the power on -3? If you had to write a power for the -3, it's to the first power, right? So is the 3 or the -3 really all that sad about being in the numerator? How about the x? Yeah, it really doesn't want to be there, does it? So how do you fix this then? So it's a -3. I like to put negatives in the numerator. That's personal preference. Over x to the 4th would be your derivative. So just for fun, let's just pretend we had that problem we had the other day. I think it was this. Isn't that the one we had so much fun with? Getting common denominators and everything. Well, let's just rewrite that one quick. It'd be x to the -1, right? So let's take the derivative nice and quick here. -1, x to the, which is the exact same thing we got the other day. Took a whole lot more work the other day, but it's the exact same thing we had. Okay. Right? So, gotta appreciate the shortcuts. Whoa. Boy, these were all, this was fun too. You had to put x plus delta x, take it to the 4th, and x plus delta x to the 2nd, take it times -3, add 7, and all the stuff crossed off, right? Yeah, this is way easier. The nice thing is if you have adding and subtracting between, you agree there's no division or anything like that, right? There's just terms there. It's so nice you actually just get to take the derivative of each term separately because it's set up that way. Now, if there was a big divided by x plus 2 or something like that, then we'd have a problem, but that's for another day. These are 3 completely separate terms, so you can just take the derivative of them separately. So what's the derivative of this term? 4x to the 3rd. Careful on this one. -6x, I've been told. Do you agree with that? Okay. And what is the derivative of that term? Very good. I wanted to see what people were going to say. It's a constant. Agreed? But it's been a while since we did a constant, so I wanted to see what you were going to tell me. The derivative of any constant is 0, so we're done. I'd like you to try example 5 on your own. They are still 3 separate terms, so they can be done separately. Well, I think that's probably enough time to see what you came up with. First thing I would do is probably rewrite that thing so it gets to a point where I can take the derivative. How do you know I'm not taking the derivative right now? Yeah, I didn't put a prime. I'm just rewriting it. I would like to take a look at this first term like that. It's the same thing. -3 x to the 3rd. It's the same thing. This next one I would rewrite as plus 3 pi x to the -2, and then minus 2x. So I'd start by doing that, and then you can go back and take the derivative. So now you'll know I'm taking the derivative because there's a prime there. Again, this is some solution to a limit problem that deals with the slope. And so I can take that 3 that's right up there, and maybe we'll put some colors here. Take that 3 times that. Agreed? Well, what is -3/5 times 3? Yeah, -9/5. Not a trick question there. All right. -9/5 x to the 2nd. Got to take it down a power. Now, 3 is just a number, right? What's pi? Just a number, right? Pi is not a variable, is it? The only variable is the x, right? So you take this -2, once again, maybe we'll color code things. Take this -2 basically times 3 pi. -6 pi, right? And then x to the, be careful, -3. Very good. How about that -2x thing there? Well, -2x to the 1st, right? So it'd just be -2x to the 0, right? Which is just what, right? The x to the 0 is just 1. So if we go back to clean this up a little bit, is there really any problem with this first term? Not really. You can leave it like that if you want. I have a slight issue with this term. We'll make it happy. And then you told me that x to the 0 is just 1. So it's -2 times 1, right? So be -2. There it is. Imagine how much fun that would have been doing the definition. Pi in there and over 5, and that would have been spectacular. Yes? I would strongly recommend you do for what we'll be using it for in the near future. The question was, do you have to make it happy? And I said yes, for what we'll be using it for. Good question. I don't know, some slacker. All right. This is a different question. And if you truly understand what's going on, it'd be a very simple question. Does the function right there, x to the fourth minus 2x squared plus 2, have any horizontal tangents? It says if yes, where? Can anybody like translate that question? Okay, does it have a horizontal slope? Right? That's kind of what it's asking, right? Because it's the slope of the tangent line comes from your derivative. Well, why don't we take a look at that graph and then we'll go from there and see if we can somehow figure out where those are. So if you take a look at that graph, I'm pretty sure I don't have it in here. Nope. If you put in 0, do you agree you would get 2? 0 for x. Okay. You put in 1, you get 1. Put in -1, you're going to get the same thing. Put in 2, you get 10. -2, 10. There you go. Little W. Do you see any places that would have a horizontal tangent? Yes or no? Yeah, how many do you see? I see 3. I'd say, wouldn't you agree that as these come in this way, they do work towards that? And as these come in, well, it's the same thing. Well, where's the third one then? Yeah, kind of right in the middle there, right? It doesn't take long for it to change around there in the middle. So you're telling me, if we just look at this graphically, there's 3 answers. And do you agree we pretty much know where they are, right? So let's do it algebraically, because we know the answer now. Now let's get to the answer. We know they're at -1, +1, and 0, right? So wait a minute. We want to find out where it has a horizontal slope. So what would probably be something very good to find? The derivative. And let's face it, if we had to do definition, that'd be a pain. But you got shortcuts now. So now we can start applying the derivative. So y prime is 4x to the third minus 4x. Yeah, plus that's it, exactly. Because there's constant, right? Which means 0. Okay, so that's great. Now remember, so far we've been using this. I would then tell you an x value, correct? Now what if I didn't see the, obviously an x value I'm going to try is 0, right? Because we see it over there. An x value I would try is -1 and +1 because we can see it. But what if you couldn't see it? What if this function was way too complex? Then what would you do? Okay, you could sit there and guess and check, or we could actually algebraically figure this out. Set what equal to 0? Why would we set the function equal to 0? Because what does this stand for? Slope. What do I want this to say when everything's said and done? Do you agree I want it to say whatever that slope is right there? So could I really ask you for where's the slope 12 on this graph? Could I ask you for that? Yeah, and you would in here, you would put 12. But I'm not asking you for where's the slope 12. I'm asking you for where's the slope horizontal. In other words, where's the slope 0? So you say, all right, wherever I'm supposed to put slope, I'm going to put 0 instead. And then you put it over here into your derivative because that's also talking about slope. So this is saying slope 0. This is saying general equation for slope. Well, those two seem to match up fairly well. And now you work on your factoring. Well, you can't really do key number because there's not 3 terms. But you can take greatest common factor, right? There's at least what in common? There's a 4 and an x in common, agreed? Once you're done with that, well, you take this 4x to the third and divide it by 4x. Well, the 4 divided by 4, that's pretty straightforward. That's just 1, right? But x to the third divided by x is x squared. Now, be careful on this one. Why is it minus 1? Because negative 4x divided by 4x is negative 1. Do you agree with that? Now what operation, though, is snuck right in here, though? Times. So all I have to do is make one of those two 0, correct? 0 times something else is going to be 0, right? So I can set 4x equal to 0, right? And I can set x squared minus 1 equal to 0, but this only works when it's 0. Don't try this when it's some other number. Okay, because all I have to do is make this say 0, right? 0 times whatever number that ends up being works. Or make that say 0, because 0 times this, whatever that number is, will be 0. Well, I think this one on the left here is pretty easy to know what that answer is. X equals? Do we agree with that? Graphically, do we agree with that answer? An x value of 0 give us a horizontal tangent? Yep. And how would you solve this? You could do a difference of two squares if you wanted to, but if I were you, I would just add the 1 to the other side, take the square root. But then you have to remember that we decided to take the square root. So, and do we agree with those two answers? Okay. So do you see how I switched there a little bit how we've been using derivative? Up until now I said, here's an x value, go find the slope. And so we substituted in for x. Now I said, find this particular slope. So we substituted in for where slope should go, which is your y prime or your f prime of x. That is slope. And this is the function that will tell you that this is the derivative, which will give you the x values that will make that happen. Okay? So it can go in both directions. But I like this one because the graph was pretty simple. We could find the answers and then prove that those were the answers over here. So they are any questions on that? I've only got one more thing I need to say, and it won't take long. What if an example 4 here, and it didn't matter which one I chose, I just chose this. What do you suppose that means? It's double prime, right? Which means take the second derivative of the original, or just take the derivative again, right? Because if you already have the first derivative, just do it again. And so for this one, what is the second derivative for this one in red we've got here? 12x squared minus 6. If you agree, most functions that are simple like this, you can take the derivative for quite a while, but eventually you will get to 0. You know, if you kept taking derivatives of simple functions, like eventually everything's going to start going away. Because you notice what I told you that you didn't really have the knowledge of the other day, that if you had x to the third, that the derivative would have to be x squared. Remember, I told you that on that one, which is why I accepted the 2 answers that one time, because you didn't know that that x to the third graph couldn't be the answer. Okay. Nope, because it's negative 6 to the first. Right, so you take 1 times negative 6 first, and then x to the 0, but x to the 0 is, so it's negative 6 times 1. Yep, okay. Yeah, but ask, that's what you got to do. Okay. And here's one of the reasons. Let's say this was the problem I gave you. Do you agree that's a line? What's the derivative of that going to be? Because the slope's always going to be negative 6. Okay, because it's a line with slope negative 6. Okay. That's the first one I made you do something similar to that. I made you find the slope of a line using derivative. Yeah. So any questions?